So let's briefly go over curl and divergence. This is 16.5. Essentially, the curl of a vector field tells you the rotation of it. So if you look at this vector field here, it's obvious that it rotates this way. But how can you show that mathematically? And in which direction is the curl pointing? For example, it's going clockwise. So if you do the right-hand rule, the vectors will be pointing toward into the paper. If it goes counterclockwise, then the curl vector will be pointing out. I'm not talking about the vectors here. I'm talking about the vector, the curl vector. The curl vector is the cross product. Now the divergence tells you, so like here, let's just talk about the curl for a second, and I'll come back to these once I define it. The curl here, like if there's a little paddle wheel here, right? There's a little paddle wheel. It looks like it's going to be turning in this direction because these vectors here are bigger than these vectors here. So it's going to be turning slightly in that direction. If you put the paddle wheel here instead, it looks like it's going to be turning in the counterclockwise direction. All right. So we'll look at the curl for this vector field in just a minute. And now, when you talk about the divergence will be how much of a source a vector field is at a certain point. So if you look at this point here that I'm drawing, not much of a divergence from this point out this way, wherever it's pointing, but there's a lot of divergence up here. Notice how much it's going, the vectors are, notice how big the vectors are from that point. Now they're getting smaller and smaller as you go, so the divergence here will be negative. We'll call that a sink in a minute. And then if you look here on this side, they're getting also smaller and smaller. Looks like the divergence might be negative everywhere on this. We'll see. So anyway, so let's define them first. So the curl of a vector field, so the curl of f, that's CRL of f, is the gradient across f, and the divergence of f, the vector field, is the gradient dotted with f. So this gradient, the del operator, it's the del operator. So an operator is a function that works on functions, not numbers. The del operator is this one here. It's the partial with respect to x, partial with respect to y, partial with respect to z, like this. So when it acts on a vector, and as far as cross product, it forms another vector, and dot product, it gives you an actual scalar. All right, so let's see this in practice. Let's just take a vector function. Let's do, I don't know, x, y, z squared or something like this. So when you do the curl of f, you do I, j, k, just like before, and then partial with respect to x, partial with respect to y, partial with respect to z, and then you write your vectors here, your vector components. And now when you do the cross product, I'll just do this without really showing you what I'm doing. This will be 0, comma, 0, comma, 0. Oh, that's great. Okay, so what happens is we got the curl of f is 0, so this is the 0 vector. So when that happens, we say, as long as we're on a simply connected region, we say that f is conservative. All right, f is conservative. What's going on with it? F is conservative if curl of f is equal to 0. So we've already seen why it's advantageous for f to be conservative. So before we show you an example of this, let's go ahead and find the divergence of this vector field, x, y, z squared. So the divergence of f is going to be that gradient operator, x partial with respect to y, partial with respect to z, and then we're going to dot that with x, y, and then z squared. So we get, looks like it's going to be, no, it's not a vector, it's going to add them, so it's going to be 1 plus 1. So it's what I'm doing here is I'm doing the partial with respect to x of x plus partial with respect to y of y, and then plus the partial with respect to z of z squared. So we get 1 plus 1 plus 2z, like that. All right. So what this says is that apparently for every point in the plane, the divergence is going to be this. So, like for example, if you have a f of let's look at point P. P is I don't know 0, 2, 7. So then the divergence at that point, divergence of f at P, will obviously be 1 plus 1 plus 14, so it's a 16. Now, if the z component is 0, the divergence is just going to be constant. So apparently, for this vector field in the xy plane, in the xy plane, the divergence is going to be constant. So maybe we can graph this. Yeah, so I plotted it using Wolfram Alpha, and so if you notice, here's my vector field. Notice how I'm plotting plot vector field like that. You can plot it real simply. The only problem is you can't move it around unless you remember. But anyway, if you notice, the z components are pretty small. The divergence here is pretty small here. The divergence measures how much it goes from a point. So if the divergence is small, the vectors are going to be pretty small in that area. So the higher the z values are, the more the divergence is. So the more outward it goes. All right. Okay, so let's look at a couple of examples here of this here. Let's look at this example here. This vector field is so it's f is y comma negative x, and then comma 0. I'm going to put a comma 0 there. It's not in there, but it's implied because it's a planar vector field. So if we do the curl of f, then we're going to do this ijk business again, and then partial respect to x, partial respect to y, and then partial respect to z. And then we're going to put the vector right below it, y negative x 0, like that. And now when we do the curl, we get, it looks like it's going to be 0, and then 0, and then negative 1 minus 1, which is negative 2. So 0, 0, negative 2, like that. So the curl is a vector that shows you what the circulation is. So apparently there is some circulation, and the circulation is in the negative z direction. So when you do the right-hand rule, if you imagine doing the right-hand rule, it's going down into the page, and the curl is the same everywhere. The vectors are big over here, but the curl is the same there as it is here. Remember, it doesn't look like it depends on x or y. This doesn't depend on x or y, where you're at in there. Now let's look at the divergence of this. So come back here. So the divergence of this vector field, divergence of f, going to be the partial with respect to x here, so that's 0. Partial with respect to y, that's 0. Partial with respect to z, that's 0. So the divergence is 0. So what this says is, at any point in the plane, the vectors going in are the same length as the vector is going out. Let me do this in a different color, red. So the vectors coming out of it are the same as the vectors going in. Same over here. The vectors going in are the same as going out. The vectors going in over here are the same as the vectors going out. So the divergence is 0 because there's no source or sink at any point. All right. A source would mean, so a source would mean that at a point your vectors are small going in, large going out. It's a source of something. A sink instead, so a sink would mean that your vectors going in are larger than your vectors going out, like that. Okay, so a source, so a sink would mean the divergence is less than 0, and a source would mean that the divergence is greater than 0. We'll talk about that in a second. All right, let's look at this one here. Let's talk about the divergence in the curl here. Looks like the divergence is going to be 0. So this vector here is f equals, looks like there's just a y component, 0, negative x squared, and then 0. This y hat, this means this is your j. All right. Anyway, so let's do the curl first. The curl of f, and it's going to be partial with respect to x. Get this smaller. Partial with respect to y, partial with respect to z, and I'm going to put these guys underneath it, like that. And now what we get out of this is, all right, I'm going to get 0, 0, negative 2x. So the curl's not 0 and it depends on x. So the further out you go in the x direction, let me do a different color. So I'm looking at this here. The further out you go in the x direction, this is 0, 0, in the x direction, the more the curl is, and it's in the opposite of the x value there. So so like at here, let's say this is 3, 4 right there. It's about 3, 4. The curl will be the x value multiplied by negative 2, so it'd be negative 6. At 5, 4, we're going to look at the x value, so that would be negative 10. So the curl here is greater than the curl here, which you would expect, because if there's a little paddle wheel here, it's going to turn more over here than it will here, okay? And it's going into the page here because it's these negative values. Over here, let's say I'm at this point over here. Let's say this is negative 3, 4. The curl is going to be 0, 0, and then positive 6. So this is going to go counterclockwise, because if you do the right-hand rule, your thumb points out of the page. And so let's see why. So if you have a little paddle wheel there, like this, you can see that the vectors are bigger on the left than they are on the right, and so it's going to go this direction. And sure enough, the curl here would be positive because the x values are negative over there. And so, like for example, at negative 3, 4, the curl would be 0, 0, 6. So positive there. Z goes in the positive direction. So if you're looking at this in 3D, basically your curl vectors are point up on the left, of y. This is the y-axis, x-axis, z-axis, and they point down to the right of y. So study that if you want. All right. So yeah, that's right. Now let's look at this one here. This one here. The divergence of f will be 2x plus 2y plus 0 if you want. So what this says is that if you pick a point in the plane, like let's say we're at 1, 2, 3, 4, 5, comma 3. So here's 5, 3. Your divergence is going to be 10 plus 6, which is 16. So the divergence, there is some divergence here. Now let's pick further out at, let's say, 10, comma 3. So at 10, 3, at 10, comma 3, it's going to get bigger, so that's 26. Yeah, it looks like it's going to be bigger there. Now let's look over here on the left side. Let's look at maybe 1, 2, 3, 4, 5, 6, 6 up. I don't know, let's just say that's 7. I don't know, 6, 7. Divergence of f at -6, 7. So now we're going to use this. There'd be -12 plus 14, that's 2. So it's still a source here, but it's going to be much smaller than the ones over on this side. So now let's pick something that's closer in, like here at, let's say that's 1, 2, 3, 4, 5, comma 2. The divergence of f at -5, comma 2, that'd be -10 plus 4 is a -6. -6. So what happens there is that this is now a sink at this point here. This is at -5, comma 2. It's a sink because the vectors to the left going into it are smaller than or bigger than the vectors coming out of it. So that's a sink. So once again, if the divergence is less than 0, we have a sink. All right, so that's easy enough to see if you get it. The question in the homework though was this one: determine the divergence and curl of this without even knowing the formula for f. So let me cut that out and paste it, and we'll look at it. Okay, so here we are. So let's look at the divergence first. All right, so the divergence of f, and let's suppose that f is PQR. Now r in this case is 0, so that makes things easier. All right, so here we are. So the divergence of f will be, so once again, it's a partial respect to x, partial respect to y, partial respect to z, and you're going to dot that with your vector p, q, and r, 0, like that. Okay, so here we get partial of p with respect to x plus the partial of q with respect to y plus 0. So it's just this. All right, so let's see what the divergence is here. In this vector field right here, if you look, so p is all the x coordinates and q is all the y coordinates. So if I'm looking for the partial of p with respect to x, it looks like the x coordinates are getting bigger as you go to in the x direction. So the x coordinates are getting bigger as you go. So like for example, this vector here would possibly be like, let's say it's 2 comma 0, and over here this might be something like 4 comma 0. Looks like maybe twice as big. So in the x direction, the x's are getting bigger. So the x's here are getting bigger in the x direction. So the partial of p with respect to x, this is greater than 0. Now let's look at the y values as we go in the y direction. So if you go in the y direction, now the y values are going to be, it looks like they're getting bigger as you go. For example, if the bottom one is 2, 0, and this top one, that would, if you look, the x values aren't changing in the y direction, but the y values are. So for example, this top vector might be 2, comma, and then we're going to go up some. So it looks like it may be, maybe, I don't know, 2, comma 4 has a slope of 2. This bottom one is 2, comma 0. So the y values are getting bigger in the y direction. So this one is also going to be greater than 0. So it looks to me like the divergence here is going to be greater than 0. Okay, now let's look at the curl of f. Okay, so this will tell us if there's any circularity around this thing. Okay, so the curl of f is, let's see. So we're going to pick this vector here. We're going to cross it with f. So the f is just pqr. R is 0 in this case. So I think I've shown this to you before. This is just 0, 0, and then the partial of q with respect to x minus the partial of p with respect to y. So check that out. All right, so we have to see what the y values of the vectors are doing in the x direction, and the x values, this is the x values, remember f, that's x and then y, right? X coordinate, y coordinate. And then what are the x values doing in the y direction? So let's see. So let's look at partial of q with respect to x. So the y values in the x direction are aren't doing anything, because if you look, the y value is going to be the height right there, and the height isn't getting any bigger. So for example, if I look at these vectors here, this first vector could be something like, I don't know, 2, comma 2. And then this last one here, now the x is getting bigger, but the y isn't. So the y values stay constant. So the partial of q with respect to x is going to be 0. Now let's look at the partial of p with respect to y. So now we're looking at the x values as the y as we go up in the y direction. And it doesn't look like anything's changing there either, because if you look at this last column here, the x values stay the same. The x values tell you how long it is in the horizontal direction. So if this bottom vector, let's say this bottom vector is, I don't know, 4, comma 0, this top vector, well, the x coordinate isn't any bigger than the x coordinate here. So that one may be like 4, comma 2 or something. And so the x values don't change. So the partial of p with respect to y is also 0. So here the curl is equal to 0. The curl of f is 0. Is equal to 0. So what that says then is that if you had a little paddle wheel here, like this, little paddle wheel, then this isn't going to turn at all. It looks like it's just going to go straight up this way. If anything, it's not going to, so there's no turning, no circulation. So the curl tells you about the circulation of the vector field. All right. So I'll tell you what, I'll go ahead and do another example from the homework. Okay, so this one, we also have f is just p, q, and 0. There's no z coordinate in this. So it looks like the divergence is going to be less than 0. And the curl, there's no circulation here. It looks like the curl is going to be 0 as well. Curl of f is equal to 0. Let's look at the divergence. So the divergence will be partial of p with respect to x plus partial of q with respect to y. So we look at the x coordinates going in the x direction. So the x coordinates are all 0 for these vectors. So for all these vectors, there's nothing going on in the x direction. So this is just 0 automatically. So p is 0 in this case. Q, what's going on with the y values going in the y direction, going up? Well, it looks like the y values are getting smaller. So for example, this one here could be 0, 4, and this one up here could be 0, 1. So of course the p values aren't doing anything, but the q's are. Q's are getting smaller. So the change in q with respect to y, remember q is the y coordinate of the vector field. This is going to be something that's negative. So the divergence is negative. Divergence of f is less than 0. Now the curl of f, once again, is going to be what we found out from the other one, 0, 0, partial q with respect to x minus partial p with respect to y. So is there any change in the y values as we go in the x direction? The y values going in the x direction. No, there's no change in the y values as we go in the x direction. These vectors are all the same height as we go in the x direction. So that'll be 0. And we saw that p was 0 in this case. Remember, p was 0. None of these vectors are sideways at all. None of them are diagonal. They're only straight up and down. So that's just 0 as well. So also the curl is 0. Curl of f is 0. All right. Now let's look at this one. It looks like the divergence is going to be 0, and the curl, I'm betting that since it's going the circulations like this, the curl is going to be less than 0. Let's check. So the divergence of f is partial p with respect to x plus partial q with respect to y. So what's going on with the x vectors, the x coordinates of the vectors, as we go in the x direction? Well, the x coordinates aren't changing at all. For example, if this, let's look at the top ones. If this vector here is, let's say 2, 0, then this vector here looks exactly the same. It's 2, 0. So the x coordinates aren't changing at all. So this part here is 0. Now let's look at the y coordinates going in the y direction. So in the y direction, the y coordinates aren't changing either because there is no y coordinate. In this case, q is 0. None of the vectors are diagonal, so there's no y at all. So here q is 0, so the divergence is just 0. In other words, this vector field f is just p, 0, 0. All right, so now let's look at the curl of f. So the curl of f, like you know by now, this is 0, 0, partial q with respect to x minus partial p with respect to y. This one's 0 because the q's are all 0. So now we just look at how the x's are changing with respect to y, and we put a negative on it. So how are the x's changing with respect to y? Well, it looks like if you go, the x value going in the y direction, it looks like it's going from negative to positive. So for example, if you just look at this column here, right here, so that bottom one might be like -1, 0. And then this top one, this might be, it looks like it's about the same, like maybe a little bigger. Maybe that's 2, 0. So as you go from the bottom to the top, as you're going in the positive y direction, the x's are changing in a positive way. So the partial of p with respect to x will be greater than 0 here. The x values, I'm sorry, the partial p with respect to y, are changing in the positive way going in the y direction. So when we go down here, this thing here is positive. We took a negative on it. So the negative times a positive is a negative. So what this says is that the curl of f is going to be 0, 0, and then something negative here. So that means that it will be less than 0. All right. So curl of f is, it's not necessarily less than 0. The the direction is negative. So the direction is negative. Yeah. And so let's see why that happens. Well, let's erase all of this. If you have your little paddle wheel in here, like this, then these vectors will be going like this and then like this. So it looks like the paddle wheel is going like this in that direction. Paddle wheel is going to go like this. And if you do the right hand rule, it's going into the page. So if you were going to look at this in 3 dimensions here, your vectors are going like this, and then they're going like this here. And so if you have your paddle wheel there, like this, then it's going like this. And if you do the cross product there, the right hand rule, your vectors will be pointing down, like this, down. So 0, 0, and then something negative here, like that. Okay? All right, so what you can do, what I would recommend you do is pick some values here, like try to figure out what p could be, and go from there and actually do the curl. All right, so let's see, is there anything else in here that we need to know? If the curl is 0, then if the curl of f is 0, then the vector field is conservative. This is if f is defined on it. The region in which f is defined is simply connected. That means it has no hole. So if you have your region and there's a hole in the middle, then curl of f equals 0, meaning f is conservative, does not apply. But if we don't have that, then we're okay. And then if f is conservative, then the curl is 0. Read about this. If it says if the divergence is equal to 0, then the fluid is called incompressible. So basically you have, if you just have all the same vectors going in the same direction, and if there's no divergence at all, the fluid's incompressible. They talk about sources and sinks here, and then they look at Laplace's equation, which you'll find out all about in diffie Q. And then if the vector field is conservative, show that it is. You just find the curl of f, and then you find a potential function there using the methods that we had before. And then we have vector forms of Green's theorem. This actually isn't too bad. Green's theorem, if you're looking, let's look at this for a second. It says basically this. We're going to get to that later on anyway, so we may as well look at it. If you look at the integral over c of f dot dr, Green's theorem says that this is double integral over d of the partial of q with respect to x minus the partial of p with respect to y dA, right? So what it says there is that what it said up top was that this piece here is just the double integral of the curl of f dotted with the k vector dA over d. So let's see why that's the case. We're going to get to this later, so let's look at it. So if you look at the curl of f, and f is PQR. This is just real brief. So this is I, J, K, partial. I tell you what, I'm going to pause the video and do this. What I've done with this curl is I've done the curl and I've written these differently. This first one here is partial r with respect to y. This is partial q with respect to z. Subtract them. And all this partial stuff gets in the way. And so just like we wrote partial of f with respect to x is f sub x, and then partial f with respect to y, we wrote that as f sub y. I'm doing the same thing up here. Partial r with respect to y is r sub y. Okay, now if I dot this with the k vector, 0, 0, the k vector is just 0, 0, 1. If I dot this, I get 0, because this times 0 is 0, plus this times 0 is 0, plus, and then this is a qx minus py. Well, that last one is just partial q with respect to x minus partial p with respect to y. So that's what's just right here. So I took the curl of f, I dotted it with k, and I got that. And so this is just another form of Green's theorem. They're identical, it's just writing it differently. This probably gives us more information about the vector field because we're dealing with the curl of it, circulation of it. All right, and so that's about it. And then we have Maxwell's equations. These are nice little bonus problems. And then this is in the WebAssign here. Okay, so that does it.